Welcome to today's lesson. Today we're going to be looking at integration by substitution. I thought I'd throw a couple of things together just to maybe explain that previous video if you've watched it. This question here, I want to make sure you understand you don't need to use substitution if you see another method. For example, I look at this and say, hey, this is f dash x over f of x. I know that when I do the integral of such a function, that is simply going to equal ln of f of x. Okay, that's cool. So here you're going to say, well, that's ln of x squared. Okay, because the derivative of x squared is perfectly 2x. There's no modification needed. Now, I would do it that way, 100%. But substitution works when potentially you find the derivative of x squared and it's not 2x. It might be x. It might be something different that you're not sure of. We can still use substitution to solve those kind of questions. So you're not having to kind of figure out, do I need to halve it? Do I need to double it, etc. So I want to show you with an easier question, which this is, what U method means. U method looks at where the parent function is. In this case, the parent function is x squared, and we let U be that parent function. I'm going to rewrite this as 2x over u dx. But the main issue is here, we can't derive 2x on u because we have two different variables. We're doing it with respect to x, so I can't have that. So we're going to modify it slightly. Now, the process that you can do, there are a couple of different ways. I like this method, okay? I'm going to work on that u equals x squared. I'm going to say, well, what is the derivative of u? Well, du on dx would equal x squared. Okay, so not x squared, 2x. Okay, so du dx equals 2x. Now, from that point forward, you could potentially substitute that 2x, okay, that 2x up there for this du on dx. What I mean by that, you could say potentially like this, du on dx all over u dx. Now that starts getting really, really fiddly and it looks difficult. Sometimes it works really nicely and other times it doesn't. If you know your algebraic manipulation, you can do it, then cool. But I think it's easier to actually say, rearrange to get what dx is equal to. So I'm going to multiply dx across the 2x. I'm going to divide the 2x across, so I get dx over equals du over 2x. Now what I find easier, I can substitute these two things. Now, if you do it properly, what you're going to see is the following, because I know you're still saying that, sir, you've still got the 2x in there, or in the u, they're still different. But when I write it like this, what happens? What do you see? Well, the 2x's can simplify, and we're left with this version of 1 on u du. And now we can see we've got one variable where we're going to derive in respect to u. Now we look at that and say, hey, I know that's a log function because the derivative of u is 1. Okay, so it's just ln u, okay, plus c. Once I've got that, I can then replace the u with the x squared, ln x squared plus c, and I've got my job done. Now, I know what you're saying there, Jens. Why would you go through all that? It was so much easier in that first point, and absolutely it was. I'm just showing you how it works. Let's look at another question. Okay, now, if I look at this, all right, we get, I look at the log function of x cubed. So the derivative is 3x squared. I don't make what's on top. Now, again, it's not that much difficult to see. Well, hold on. If I do the derivative of f of x on the bottom, okay, and I do that f dash x over f of x, we're going to get x cubed and 3x squared on top. Well, all I need to do is I need to double my function. So it's going to be 2 ln x cubed. Again, if you get that, then that's really cool. But watch what happens when I deal with u method. So my parent function is the x cubed. So let u equal x cubed. I'm going to find the derivative of u to make it 3x squared. Okay, I'm going to rewrite this, of course, as we go through. And this is where I'm going to go further to make dx the subject, which is du on 3x squared, because now what I can do, I can replace the dx with this du. Now, when you do that, look what's going to happen here. Du over 3x squared, can you see now we are going to simplify? We can simplify the 6x squared divided by 3x squared. Well, that is equals 2. So I'm left with 2 on u du. Now, again, from that point, you can find the integral pretty easily. But what I'm going to do, I'm going to go one step further. I'm going to take that 2 out the front because it's just a number. Okay, whatever my answer is, I'm going to just double it. Okay, it doesn't matter where it is, but I like having it out the front because it makes my function easy on the inside. Now, all I'm going to do is do my integral, okay, which will be 2. Now, it's going to be ln u because we know that's the derivative on top, plus c. And the last part, I'm going to simply sub in our x cubed back into that function as such, plus c, and we've got our answer. Now, again, I said the beginning part, okay, that you could probably see that all you have to do is double it, and you can see that works out, okay? But this works for all cases. I'm going to scroll down to something that gets a little bit nastier. Okay, I'm going to look at maybe something that looks like question 4. Okay, question 4 certainly looks a lot nastier, okay, than what that previous one does. So I often use U method questions or substitution when it's really, really funky. We've got this thing that looks like a quotient rule. The bottom part doesn't make what's on the top. So it's really quite nasty. It's probably going to be a log because it has to be a log, right? That's all we've learned how to do that. So let's try to use the U method. I'm going to let U equal that parent function. Now, what I'm going to do here, you can let it equal the whole thing on the bottom, okay, or you can let it equal this thing inside here. Because remember with logs, it's the f of x, it's underneath, that's what you're letting that derivative be. So what you can do is something like this. Let that equal x squared plus 4x minus 3. Okay, now I'm going to find my derivative. I mean, you can let the square, but the derivative is going to be harder. In this case, it's going to be nice and easy. 2x plus 4. Okay, that's my du dx. I'm going to now write du dx. So dx equals du all over 2x plus 4. Now, I'm going to go back into my integral of x plus 2, put my u squared now dx as such, and I'm now going to replace my dx with that variable we found. X plus 2 all over u squared times it by du all over 2x plus 4. Now, you look at that, I know what you're saying. Well, how do you simplify 2x plus 4 and x plus 2? Well, maybe what you might recognize, okay, that the 2x plus 4 can be written as 2 outside of x plus 2. And now look at that's my link. Okay, my link is x plus 2 and x plus 2, they can cancel out. So we can now write it as 1 on u squared. Okay, well, it's a 1 on 2u squared. Okay, du as such. Now, again, I'm going to make things easier. I'm going to pull that half out just to make life a little bit more simpler and have 1 on u squared du. Because I think that integration is going to be easier to do on 1 on u squared as opposed to 1 on 2u squared. That's personal preference. Now I'm going to integrate. Okay, now I might rewrite this because I like u negative 2 du better in decimal form. So my last section here, gents, is now I'm going to integrate. I'm going to now say equals a half. I'm going to say, let's go u negative 1 divided by negative 1 plus c. Okay, now you might say equals a half and then put the negative 1, the u negative 1 down the bottom. So we're going to say 1 on negative u as such, because what that is, plus c. You might pull the negative out the front as such. Okay, we can do that. And now all I need to do is I need to sub my u back in. 1 over. Now, what was our u value? Our u value, of course, was had x squared plus 4x minus 3. So x squared plus 4x minus 3. Bang, plus c, and we're done. If you want to multiply it out and put it as like this, for example, negative 1 all over 2 brackets x squared plus 4x minus 3 plus c, you can absolutely do that as well. Gents, this is not easy, okay? And I've done a whole lot of working out for you for all these questions. You can have a look at the video that I put up, the very first one, but I've put worked examples for all of these. What you may or may not notice sometimes, gents, that you might find there are slightly easier ways to do things. I'm just going to make this nice and big so you can see it. Okay. Let's have a look. I'm going to see if there's a one that can explain this. I like this method, by the way, for every single question. I really like it. But look, here's one here, right? See this one here. You've got the 3x squared, and that is the actual derivative. There's no modification happening to it. Now, you may have seen that early on, but you might not have. But instead of actually rewriting the dx and subbing the dx in, you could, in fact, sub 3x squared for the du over dx, which means that the dx and dx would cancel, and the du sits there, and it's just a nice integration. So there are other methods, but I do like this method. This is not the one the book uses, but certainly it's the one that the IB Revision Village uses, and it's a really nice way to do things. Every time you're recognizing the parent functions up here, it's the x cubed plus 1. Okay, the next question, recognizing that this is the one that's been differentiated, the sine 4x. Okay, so again, we're going to rewrite it and let it equal u. That's a sine ux. You can keep the power in or out. It's way easier to keep the power out, let me tell you, all right? It's much easier for the differentiation. Again, this one here, you can see whatever's in brackets. There you go, x squared minus 3. Let's pull that out. In question 5, 2 plus x to the power of 4. Let's pull that out. This one here, it's what's in the brackets, the x squared plus 3. Let's pull that one out. So pretty much whatever's in brackets is the easiest part to do. Okay, you pull it out, get an expression for d dx, rearrange it to make it dx equals, sub it back in, simplify, and then once you have your simplified version of your integral, we integrate. I hope that kind of makes sense. I know it's really hard, me not being in the classroom, but that's just the way it's got to be. Have a crack at those videos today, gents. Have a crack at some of those questions, and I'll be outside.